Hi there. So this was supposed to be part of the Sony video, but I've decided to do it as its own video. You'll have to excuse me. During the middle of a global pandemic, I've managed to catch a cold. Anyway, so those keypads and displays on the Sony video control panel are all driven by shift registers. There are 3 wires for the keys, 3 wires for the LEDs, and 3 wires for the displays. In the case of the keys, we're reading data back. In the case of the LEDs and the displays, we're sending data out. So, quick look on how to do that. If you're doing work with Arduinos, PICs or anything like that, this is a handy thing to know because it's a good way of getting almost unlimited I/O pins out of your device. You can use this in either way to generate data to go into a micro or just take data out of a micro. So what I'll do is I have Logisim here and I'll quickly build one. You can build this out of 7.4 series logic. Logisim doesn't quite have the same parts as you would if you were building this yourself. So I will just quickly run through. So like everything with sequential logic, we need to start with the clock. And what we need to do is take our clock and we need to take that off to where our shift register is going to be. We also need to generate a clock pulse every 16 cycles, so we're going to grab a counter. Bear with me, I just need to remember where the clock goes on this, because I've not made this easy on myself here. Where's our clock? There, so we've got our clock in. Yep, goes in there. So our clock goes in and we are generating a 8-bit output. This is where it differs slightly because it confuses single bits and 8 bits. So that's going to complain. Get it in the right place. So the output of the counter is not 8 pins but 8 bits. So we need an 8-bit wide splitter to deal with it. We're going to pick bit 4, which I believe is there. Drink. And we need to grab a NOT gate. Flip that round. And wire that in there. And then our inverted goes into here. And our non-inverted goes into here. That resets our clock. So if we start simulation now, you should see this count up to 16 and then stop. 1, 2, 3, 4, 5, 6, 7, 8. There you go, and it resets. And if we bring this signal up for our shift register, that gives us our synchronization pulse. I'll leave that running. So next up we need our shift register. There it is. We're going to be different. Most 7.4 series shift registers in single packages 16 bits. You can buy bigger, you can buy larger shift registers. So the first thing we are going to need is going to be our clock. So our clock comes in there, and you can see that's just clocked out. And then our reset comes in here. And you should see that, well you won't because it's not set to load anything. Now what we're going to do is we need another splitter. That facing south, we want it right handed, we want it 16 bits wide. Boop. And this is our input. keep forgetting those are not freeform. So there you go, and let's change that to something interesting so you can see something go on in. So we'll go for OXAAAA, which will give us alternate bits, and you'll see that loading and shifting out. So if we take this out now, that is our serial data, which we need. That is our serial clock, and then we need the reset. So we now have three lines here. We've got a clock, we've got data, and we've got a reset line. We need the reset line because we need to synchronize these. Even if you are running two of these on the same circuit, they power up at the same time. The clock line could get glitched, the data line could get glitched, which results in the counters being out of sequence. The reset line controls that and stops that from happening. So let's grab our shift register for this end. Just make sure we are lined up. So we are bringing our clock in. You can see that's now shifting out. And we are bringing that in. Let's just go into the bottom there, and we've got our reset. So you'll see that now our data from this side is clocking in. We need to change that to be 16 bits because at the moment we're losing stuff. There we go, and you'll see our data clock in. Actually you won't, because I've done something wrong. Well, that's not working very well, is it? I can actually see what it is. So I've seen this before with Sim, and you have to be careful, but it is possible to join pins without realising you've done it. So what I need to do, and the only way out of this, is to pick that up. How many of you spotted that? And go back, chuck our shift register down, and we need to make that 16 bits. I will stop doing that one day, and there we go, you can see we're working now. So what we've done is we've joined the load pin somehow to the data pin, which is quite odd, but there you go, we're shifting now, that's all good. Right, as you can see, if I grab a splitter again, we'll make him north facing. Again, we need 16 bits, and set that to 16 as well. If we chuck that up there, and you'll see that as we're clocking data in, it goes along. That's not useful if you've got LEDs on there. Let's just show you that. Let's go for 16 bits again. I'm not going to do all of the LEDs, we'll do a couple. One. Although it's not that hard to do all of them, but I'm only going to do 8. There we go. This is going to be messy. I don't like messy. Let's just tidy this up. Move those up, copy them, paste them back. Okay. You can immediately see as I start wiring these up, we've got a problem. Although we've got control of these LEDs, the LEDs follow the bits through the shift register, which isn't ideal. I mean, if you imagine these were the key switch lights on that number pad, that's really not going to be very useful. I really must buy a new mouse. Now there is a simple way around this. Quite a few of the 7.4 series shift registers have a latch enable pin, which allows you to latch the content of the data. Was that me? Yes, it was. Sorry. So there is a way around this. Most of the 7.4 series shift registers have a latch enable, or you could use a 7.4373 to do it. We don't have those, but we do have register. So what we'll do, and this is where our synchronization pulse comes in handy. So we will take our data, our 16 bits of data here, which this is going to complain about. There we go. Make sure that that is 16 bits. And then this is our data out. And then what we use is the enable. So we bring our enable for the register. This would be latch enable on the appropriate 7.4 series device. And when we get our reset, let's just pop that in because that will reset the counter to 0 as well. That also helps stop some of the silliness. And you can see our 8 bits are still shifting in. But if we now break this and feed it from our register, you'll see that we're not shifting. So what's happening now is we wait until we've got our bit pattern. When we've got our bit pattern and we do the reset, I just want to check something. Yeah. So when we've got our bit pattern and we do the reset clears this. You don't really need this, to be honest. You could leave it like that. There's no reason to have that. It's just neater. We do our reset. At the same time, that enables the latch here. The latch records what we've sent over and holds it steady. So until we get this reset pulse, the LEDs do not change. So if we invert that now, oh, missed. So 5555 is the opposite of A, and you'll see on the next load the LEDs will invert. Just missed that one. Here comes our next one. Bam, and your LEDs are inverted. So that's how you do shift registers. This is more complicated than it would be. I mean, if you look, we've got 1, 2, 3, 4, 5 chips there. We've got this. We've got the pull-up. We've got the register. We've got the splitters. These are not all things that would be in the real setup, unless you wanted to do it this way. But you would generally use your counter and your shift registers. Your latch enable is generally built into the shift register. So this entire section here can be completely built into a micro done in software. So that then gives you your 16 outputs in this case with one chip. There are 16-bit shift registers. You can cascade these, so you can quite happily put let's pick up another shift register. Blink. So most shift registers have an output, so you can just shove the output of that shift register into another one, and you'll see now the data is clocking out. So if we made this a 16-bit one, let's just delete that just so we get some more room, and make that 16, and you'll see that that will become a mirror image of what's going on here. So as your data clocks out of this, it falls out the other side. If you use the reset pin, then you will find that you'll just get zeros clocking in here, because what you're clocking out of here is the zeros that has happened as a result of the reset. So what could you use this for? I mean, obviously you've got the ability here to drive your LEDs. That's actually quite a good use for them as well, quite a common use for them, for basically driving as many LEDs as you want, or as many outputs as you want over serial. You can send an address in here and then use the outputs of here to drive a multiplexer. That gives you a fourth line that allows you to select. If you use analog multiplexers, you'd be able to select an analog signal out of, in this case, out of quite a lot of inputs. 16 bits gives you more than ample analog inputs for most things. This is the basis of something called time division multiplexing. So if we left this running a counter and then drove a multiplexer here, the multiplexer driven by this, and then you've got I can't remember what the maximum value we can have on 16 bits is off the top of my head, but that gives you quite a lot of inputs. In the case of 8-bit shift registers, you've got 256 analog outputs and only using one analog pin and 4 pins to deal with it. This is quite commonly used in intruder alarms for zone expanders. A lot of people assume that the intruder alarm is with the zone expander contains another 8 inputs. It's very rare that it does. Most of them, Gardner Technologies, Honeywell and similar, actually use an analog multiplexer in this kind of setup, so that the alarm still is seeing the analog signal from that cable, and obviously it allows you to see a little bit easier that someone may have monkeyed with something. But this is what the Sony's doing, and obviously you can do this backwards, so you can generate the clock and reset pulses at this side and then send those out to the transmitting shift register, and that would allow you to read data. That would allow you to read data back. There's all sorts of things you can use it for. It's a very handy little circuit. Anyway, thanks for watching. Bye.